So is it audible? Is it audible? So let us start. So note down this problem. Find the law of force towards the pole under which the following curves are described. So in that, the first one is r square equal to 2ap and p square equal to ar, and the last one is b square by p square equal 2a by r minus 1. So for this relation, we have to find out the law of force. Now, whether it is explicitly mentioned or not, if the relation is given in terms of r and p, so this is a form of pedal. So the equations are given in pedal form. So pedal form, the differential equation of the central orbit we have derived, that is, so h square by p cube into dp by dr is equal to p. So this is the equation of the central orbit in case of pedal format, right? Now in this relation, what it was given is the first one, r square equal to 2ap or p equal to 2a by r square. So this is the p value, and then we can calculate 1 by p square value. So 1 by p square equal to, so you can square it, this is r power 4 divided by 4a square. So this is the square value. Now if you take the derivative on either sides with respect to r, so that you will be able to find out dp by dr value. So for that, if you take the derivative of it, then this is minus 2 by p cube into dp by dr is equal to 4r cube divided by 4a square. So this 4 will cancel out, and then this is minus 2 by p cube into dp by dr is equal to r cube by a square. So these two you can take on to the other side, and you can multiply h square on either sides. Then h square by p cube times dp by dr is equal to minus r cube h square divided by 2a square. Got it? Let me check it. Sorry, this was taken wrong. So P is equal to R square by 2A. So this is P. Now everything will go for a toss now. P is equal to R square by 2A. So from this relation, then 1 by P square equal to 2A divided by R square whole square. So this is 1 by P square equal to 4A square divided by R power 4. Now if you take the derivative on either sides, minus 2 by P cube into dP by dr is equal to 4A square into, so minus 4 by R cube. So this is minus 16. So minus minus will cancel and this goes 2 times and then 8A square by R cube. So 1 by P cube dP by dr equal to 8A square divided by R cube. If you multiply on either sides h square by P cube into dP by dr is equal to 8A square h square divided by R cube. The law of force is, so this is the equation of the central orbit. Got it? Understood? So in the similar manner, you can solve the other one. So P square equal to AR. That is the equation of the parabola in pedal form. So Vishal, actually question number 10 and 13, that level of complexity you don't expect. So that is actually too complex. That is actually, but the fundamental concepts are the same. And the solution of the differential equation is a little tough. So that is the only thing. Yeah, this is R power 5. I have taken integral. So the second one, P square equal to AR. Then 1 by P square you can take as 1 by AR, and then if you take the derivative of this, minus 2 by P cube into dP by dr is equal to 1 by A into, so derivative of 1 by R is minus 1 by R square. So minus minus will cancel out, and then from this if you multiply h square on either sides, h square by P cube into dP by dr is equal to 1 by 2A R square into h square. In the similar manner, you can follow the other one. So in the case of apes, right? So what happens is, in case of apes, so that is actually this is an ellipse, and then for this ellipse actually, so this is the maximum most distance and this is the minimum most distance. There actually what happens is, this is the maximum radius, and if you draw the tangent to it, this will make an angle of 90 degrees there. Now that relation, so here also if you take the tangent here, this will make 90 degrees with the radius vector, taking this as the pole. Now in case of apse, what happens is du by d theta value, it will be 0, and dr by d theta also will be 0, and the phi is the angle between the tangent and the radius vector. This will be 90 degrees. Now let us prove how it is going to be. We have got the fundamental relation of 1 by p square equal to u square plus du by d theta whole square. This was proved. And then in this, actually, if you notice, du by d theta value at the apse point, at this location and this location, are 0. Hence, this if you take as 0, then 1 by p square equal to u square, and this u square you can write as 1 by r square, because from the relation of u is equal to 1 by r. Now 1 by p equal to 1 by r, it implies p equal to r. But the p value is, p is always treated as r sin phi, where phi is the angle between tangent and radius vector. So this is the relation. So tangent and the radius vector. Now p value you can treat as r is equal to r sin phi. Then r will cancel out. It implies phi equal to pi by 2. So this is the fundamental condition of an apse. Got it? So at apse, what happens is the values of du by d theta and dr by d theta equal to 0, and phi will be definitely 90 degrees. This is the condition of apse. Got it? So you can note down this. Note down one more, this apse related problem. Try to solve this problem. A particle moves with a central acceleration which varies inversely as the cube of the distance. If it be projected from an apse, at a distance a from the origin, with a velocity which is root 2 times the velocity for a circle of radius a. Show that the equation to its path, show that the equation to its path is r cos theta by root 2 equal to a. So this is the path of the particle, provided if the particle moves with a central acceleration which varies inversely as the distance of it, if it be projected from an ellipse at a distance of a, that means p is directly proportional to 1 by r cube. So this is the central acceleration what it was given. And then, so this actually, if you replace with a constant mu by r cube, so this is the acceleration it was given. And then if it be projected from an ellipse at a distance a from the origin. Now at the ellipse actually we have the fundamental condition, that is du by d theta equal to dr by d theta equal to 0 and the angle phi equal to pi by 2. So this is the condition of the ellipse. And then at an ellipse actually, so u is equal to 1 by r is equal to 1 by a. This is at ellipse. So this is at ellipse. So the value of u value is 1 by a at the ellipse. That was the information it was given from the origin with a velocity which is root 2 times the velocity for a circle of radius a. Now if the particle is traveling in a circle, so if the particle is trying to travel in a circle with the central acceleration, then obviously this value is going to be the central acceleration, which will be given as v square by a is the central acceleration in case if the particle travels in a circle. So v square by a is the central acceleration for any circular path. So that's why actually the centrifugal force mv square by r or mv square by a is the centrifugal force, and this m comes from the fact that it is the force. And if you remove that m, this is going to be v square by a, which we call as the central acceleration. So this central acceleration value is p is equal to v square by a. Now if this is the velocity of the particle, if it is traveling in a circle, then the velocity what it was given for this particular orbit is root 2 times of that velocity. That means the velocity v1 is equal to root 2 times of v square by a. So this is the velocity. So this velocity actually we should be finding it out, right? So the velocity for a circle of radius a, show that the equation of its path is given as r cos theta by root 2 equal to a. Now can you try to solve this with this information? So this can be velocity, right? So actually in case of central acceleration actually, so if a particle is trying to move in a circular path, then actually the acceleration what we can calculate from the fundamental equation of the particle if it is moving in a circular path in any random plane. So we have derived the equation, that is so I hope you remember this. So d square r by dt square minus r into d theta by dt whole square times r cap. So this is the acceleration which is in the radial direction. Now if it is a circular path, then actually dr by dt is going to be 0. Now if it is equal to 0, then the acceleration, so this is going to be minus r omega square, where omega is equal to d theta by dt. And for any circle, the omega and peripheral velocity relation is v by r equal to omega, right? So from the velocity relation you can get it. So r omega so omega square can be written as v square by r square equal to omega square. If you replace it here, minus r times of v square by r square. So this r will cancel out. Minus v square by r is the acceleration, which we call as the central acceleration. So this is being directed towards the center, which is the decreasing direction of the radius. So this negative sign can be taken as in this direction. So, but the magnitude of the acceleration is going to be p is equal to v square by a. Got it, Pankaj? Okay, so you can note down this. We are going to solve this. See this, the problem statement, you clearly understand this. See this, a particle moves with a constant, with a central acceleration which varies inversely as the cube of the distance. That is, p is equal to directly proportional to 1 by r cube. So inversely proportional to cube of the distance. Now p can be written as mu by r cube. This is the acceleration. And suppose if the same acceleration, when it is happening, when the particle is moving in a circular fashion, then you are going to get certain velocity. Now root 2 times of this velocity you consider for the particle traveling in this particular path. Got it? That is the problem statement what he asked for. Understood? Assume that if the particle is traveling with the same acceleration in a circular path, you are going to get certain velocity. And that velocity, so root 2 times of that, if it is considered to be the velocity of the particle when it is traveling in a path which is given by r cos theta by root 2 equal to a, then that path is going to be definitely this one. That's what is the problem statement. Understood, Pankaj? Okay. So let us solve this. So the acceleration of the particle is given as p is equal to mu by r cube. So this is the acceleration of the particle. Suppose if the same acceleration, if the particle tries to travel in a circular path, so the velocity of the particle in the circular path. So let us say this is v, which is equal to a times of p under root. So a times of p under root. So and the radius is r equal to a. Now the velocity when it is traveling in the circular path is equal to a times of mu by r cube. This is the acceleration. So under root and at r equal to a. So this is going to be mu by a square under root. So when the particle travels the path mentioned is root 2 times of this velocity. So this velocity, let us say this is v1, root 2 times of v. So root 2 times of this is going to be 2 times of mu by a square under root. So this is the velocity. Now the relation or the equation of the central orbit is given as h. So u plus d square u by d theta square into h square is equal to p by u square. So this is the equation of the central orbit. So for the central orbit, let us say if you multiply on either sides to solve this differential equation, the standard method is multiply 2 times of du by d theta on either sides. This is the standard method of solving this differential equation. So if you do this, what happens is the left side one, it will become an exact equation. So this is the integrating factor with which if you can multiply this, this is going to become an exact differential equation. Now this is going to be h square times of, this can be u square plus du by d theta whole square. Now for this actually d by d theta of. So this differential, if you simplify it, you are going to arrive at this equation. So from this you can write this because this is the exact differential here. So u square plus du by d theta whole square, and this is going to be p by u square. So into 2 times of du by d theta. Now this d theta and this d theta you can cancel out, and then h square times of, if you integrate on either sides, this is going to be h square times of u square plus du by d theta whole square. So this is the left hand side, and the right hand side is going to be, so p value we just calculated, that is p is equal to mu by r cube. So mu by r cube we can even write as mu times of u cube. So this you can write mu times of u cube divided by u square into 2 times of du. So this u square will cancel out, and mu times of u into 2 times of du. So this is mu times of 2 times of u square by 2 plus some arbitrary constant a. So this 2 will cancel out, and finally what it was left over is h square times of u square plus du by d theta whole square is equal to mu times of u square plus some arbitrary constant a. So this is the differential equation without the initial conditions. So now we have to find out this initial condition so that we can simplify this path. Got it? So you can note down this. I am going to erase it, and then I will try to further simplify this differential equation. Done? So we have got h square equal to h square times of u square plus du by d theta whole square equal to mu u square plus a. Now the initial condition is the particle is projected at an ellipse. The particle is projected at an ellipse. Hence, so at the ellipse actually du by d theta value will be 0. So this is the primary thing. And then r equal to a. And so even the pedal value also is equal to a. Right? Now h square, and this value actually, if you notice, this is the velocity of the particle when it is trying to travel in a central orbit. So v square value what we have got on the left side. And then the velocity of the particle we have calculated, that is 2 times of mu by a square under root. So this is the velocity of the particle, so which was given initially. Now, so here the initial velocity was given and u is equal to 1 by a because it is at an ellipse, and then du by d theta equal to 0. So from this relation, so 2 mu by a square whole square is equal to h square times of 1 by a square is equal to mu a square plus a. So mu by a square plus some arbitrary constant a. Now from this relation, so 4 times of mu square, or actually 2 mu by a square whole square is equal to h square by a square is equal to mu by a square plus a. Sorry. So for this actually there is a root, right? Yeah. So here there is no root now. So from this relation actually you can equate these two. H square by a square equal to 2 mu by a square. So from this actually h square is equal to 2 mu, or h is equal to 2 mu under root. So this is one relation what we have got. And from the other relation, so this is 2 mu, if you put it here, 2 mu divided by a square equal to mu by a square plus a, it implies a is equal to mu by a square. So this is the arbitrary constant value. Now if you put these values of h and a in the original equation, so that is, so this one, so h square is 2 mu u square plus du by d theta whole square is equal to mu u square plus mu by a square. So this is the equation of the path. But here actually again we landed up with the differential equation itself. Got it? Yeah. So we landed up again with the differential equation. Now actually this differential equation in the form of du by d theta. So we have to solve for this du by d theta. So here actually the problem is what we are getting here, it is we are getting a second order differential equation to be solved, and that is a little complicated differential equation. For that actually we are adopting two different aspects. One aspect is you are multiplying with 2 times of du by d theta on either sides, so that you can bring into the form of the exact differential equation. And there actually you can integrate it, and then you can remove the second order differential equation and you can bring into the first order differential equation. But that first order differential equation is again first order but second degree. And this differential equation again we need to be solving after submitting the initial conditions, so that you will be able to find out the initial condition, that is a value, which is an arbitrary constant which depends on the initial values. So this differential equation we have to solve for u again, so that you will be able to find out the relation of u and theta, which is the required path in the normal algebraic equation by avoiding the differential coefficients. Got it? So there is one more step to solve this now. Got it? So we can note down this. Then so this differential equation, if you further simplify it, two mu times u square plus du by d theta whole square is equal to mu u square plus mu by a square. So this is the differential equation. Now from this actually 2 mu u square plus 2 mu du by d theta whole square equal to mu u square plus mu by a square. So 2 mu u square and this is mu u square. So du by d theta whole square equal to 1 by a square minus u square or 1 minus mu a whole square divided by a square. And then if you take the root of it, then actually du by d theta equal to 1 minus ua whole square under root divided by a. So why we are taking root is because actually we don't know how to solve the higher degree differential equation. For that actually you are bringing into a first degree differential equation. So for that you can take root on either sides. So du by d theta is equal to square root of 1 minus mu a ua divided by a. So this is, it implies d theta by a is equal to du by 1 minus au whole square under root. So now actually if I take au is equal to t, then dt equal to a times of du. So for that actually you multiply with a and then divide with a, and this a will cancel out, and then d theta equal to a times of au divided by 1 minus au whole square under root. Got it? So I think there is some 2 here. So this is root 2. So now you can integrate on either sides. So if you integrate on either sides, this is d theta by root 2. So d theta by root 2 is implies theta by root 2 plus some arbitrary constant b is equal to, on the right hand side, dt by 1 minus t square under root is nothing but sine inverse of t, sine inverse of au. So this is the equation which is an algebraic equation now. So this algebraic equation, you can identify this arbitrary constant from the initial values. So at theta is equal to 0, you can identify that as an x. So at theta equal to 0, you substitute the b value, and there u is equal to 1 by a. So a will cancel out, and this value is going to be pi by 2. So you note down this. I am going to simplify that. Now here at an apse, theta equal to 0, u is equal to 1 by r equal to 1 by a. So here, so 0 by root 2 plus b is equal to sin inverse of a into 1 by a. So this is going to be pi by 2. So it implies b equal to pi by 2. If b equal to pi by 2, theta by root 2 plus pi by 2 equal to sin inverse of au. Sin inverse of au. Now au is equal to sin of pi by 2 plus theta by root 2. Then sin 90 plus theta is cos theta and a by r. So a is equal to r times of cos theta by root 2. Got it? So this is how actually you can solve all these kind of problems, even whether it is at an ellipse or actually with certain angle. Also it will be the same procedure. Only thing is you will be substituting the initial conditions as per the requirement. Suppose actually rather than an ellipse, right? So he might give the problem statement saying that if it is projected with a velocity of v at an angle of phi or at an angle of pi by 4, like that actually he is going to give it. So instead of 90 degrees actually we take as the angle whatever it was given there. Got it? So that is the condition. Got it? Any questions on this? Any questions on this? Okay. So this is how actually, this time actually I have covered more number of problems from the central orbits, because actually, so there might be a possibility that actually you can ask the questions from these scenarios. Why? Because this is a little complicated than all other topics of dynamics. If you have any questions on this, you can ask me now. Which questions to solve? So whatever the models I covered, right? So those models are sufficient enough. So from this actually, so in Krishna series actually there are n number of problems actually it was given. So very huge number of models he has given. So it is up to you actually whether you want to try all the problems. But the models whatever I covered, right? So these are actually far important models. So these models actually if you cover it, then that is sufficient enough. But if you wanted to practice more, then actually you can try to cover more number of models. But actually the time won't be sufficient to cover all the problems, because so Krishna series statics and dynamics, two books together is only for one topic. So that you have to keep it in mind. So whatever I cover in the class, right? So these models are sufficient enough, but you can practice more problems with the same concepts. And if you notice, whatever the problems we solve, right? So it won't go out of the concepts what we have covered here. So all the problems, right? So these are actually from the concepts whatever we have discussed. Conceptually, I have given 100%. But problems actually you can try more number of problems. The complexity goes in different ways. Maybe in solving a differential equation, or actually maybe identifying the integrating factor. So maybe different paths, formation of the differential equations. So these things are the foundation things. So these foundations actually you have to be aware, so that actually you can solve more number of problems. So if you solve more models, then actually all those concepts actually will be in fingertips. That's the only thing. Got it, Pankaj? Okay, let me check that what is that problem. Okay, so you note down this. Show that the only law for a central acceleration attraction, show that the only law for a central attraction for which the velocity in a circle at any distance is equal to the velocity acquired in falling from infinite to the distance is that is that of inverse cube. Got it? So this is the problem statement. Show that the only law for a central attraction for which the velocity in a circle at any distance is equal to the velocity acquired in falling from infinite to the distance is that of inverse cube. Now actually here two different cases he has given. One case is actually a particle trying to move in a circular path with the central acceleration. This is one case. Another case is if a particle falling from infinite, what it essentially means for us. So if the particle falling from infinite means the particle started with a velocity of 0, that's what it meant by. Suppose actually if I try to leave this particular chalk piece, just a minute. So yeah, sorry. So now actually let us say if this chalk piece is left over like this. Now actually this chalk piece is having 0 velocity here and it is trying to acquire a velocity when it is moving downwards. So it started with 0 velocity and then actually it keeps on acquires the velocity. Now actually let the acceleration of this particle is going to be p, and let us see if it is constant, then actually we know that actually this p value, right? So from the relation what we have got is v times of dv by dx or dv by dr. This can also be called as the acceleration. Why? Because for any particle, so when it is traveling with a displacement of x in a time of t, the velocity is going to be dx by dt, and this is the velocity of the particle when it is trying to travel. Now this dx by dt, if I take again the derivative, the acceleration p is equal to d square x by dt square. But this relation you can also write as d square x by dt square can be written as d by dt of dx by dt, and this relation you can write as, if you multiply with dx on either sides, dx by dx, if I do it, I can take this dx here and dt here, d by dx of dx by dt into dx by dt. So this is v times of dv by dx. So this is also called as the acceleration. So this is the relation actually what we are going to use it. Now this acceleration, so p is equal to v times of dv by dx, or v dv is equal to p times of dx. Suppose if this acceleration is constant, then actually we can straight away integrate it. Then px is equal to, so v square by 2, and let us say the initial velocity is u and the final velocity is v, then v square minus u square by 2 is equal to px, or v square minus u square is equal to 2px. So this is the velocity relation. So this is actually, this you might have learned already. This is actually with the constant acceleration of p, v square minus u square is equal to 2ax or the 2px. So this is a fundamental relation for the constant acceleration. Now this methodology we are going to adapt even here also. So v into dv by dr is equal to p, where p may be a function of r. Now actually we are talking about the central acceleration. Now this central acceleration, so this you can treat as a function of r. So this is p of r. Got it? Okay, so let us continue our discussion. So now actually we have got the relation. So p can be treated as f of r. So if velocity, if you treat as f of r, then p is also a function of r, then this can be treated as dv by dr is equal to f dash of r. So this is how, this is again a function of r, note this. So g of r. Now from this relation, so dv by dr is equal to f dash of r, then p is equal to f dash of r. So this can be treated as v dv by dr. v dv by dr is equal to f dash of r, then v dv is equal to f dash of r into dr. So this is how actually you can assume. So this is the fundamental thing what you need to understand. Got it? Then actually, so this is v square by 2 and this is f of r plus some arbitrary constant c. So this is v square by 2 is equal to 2 times of, so v square is equal to 2 times of f of r plus some arbitrary constant c. So this is one relation. Yeah, this is correct. So now actually, so this you need to treat as negative, because actually he stated that when the particle is trying to fall from infinite, so at infinite actually the velocity is going to be 0. Now suppose actually if I leave this chalk piece like this, and actually so the radius or the central acceleration whatever it is dragging downwards, this is the decreasing direction of r. So if it is decreasing direction of r, then actually you have to treat that acceleration as negative. So this is the fundamental statement. So then this is going to be negative. So minus of 2 times of f of r plus c, and even here also you can treat this as minus and minus. Yeah. So minus of 2 times of f of r. So this is equation number 1. And the second statement what he said was, so when the particle is trying to move in a circular path, suppose if the particle is trying to move in a circular path, then the centripetal acceleration is going to be p, and the velocity of the particle is going to be, so v square by r is equal to p. So this is the velocity of the particle. So p is equal to v square by r in case if the particle is traveling in a circular path. So this is actually when the particle is trying to move with a radius of r. So it is trying to fall like this in a straight line manner. And this is actually, so this straight line may be 3D straight line also. So this is actually when the particle is trying to move in a circular path, there the centripetal acceleration v square by r. So this is going to be p of r. And p of r actually we have treated as p of r is equal to f dash of r. So this is f dash of r is equal to v square by r, implies v square is equal to r times of f dash of r. So this is the velocity if the particle is trying to move in a circular fashion. Got it? Yeah. So here actually as per the problem statement, so both the velocities are same. So here actually v square is equal to r times of f dash of r, and here v square is equal to minus 2 times of f of r plus c. Now if you square, so this is, if I say v1 and this is v2, then v1 square is equal to v2 square. So this is as per the problem statement. See this, show that the only law for a central attraction for which the velocity in a circle at any distance is equal to the velocity required in falling. So this is the velocity required in falling from infinite to the distance is at of inverse cube. So this is when the particle is trying to travel in this manner in a straight line, it will acquire certain velocity. That velocity is nothing but when it is falling from infinite, the statement infinite means with zero velocity. It started with zero velocity and then it keeps on moves. If it keeps on moves, it will acquire certain velocity. That value is going to be v1 square is equal to minus 2 times of f of r plus c. And when the particle is traveling in a circular motion in a central orbit, then actually the velocity is going to be v square is equal to r times of f dash of r from the central acceleration of v square by r is equal to p of r. Now these two are equal as per the problem statement. Now if you equate these two, what happens is minus 2 times of f of r plus c is equal to, so v1 square equal to v2 square. So this v2 square is equal to r times of f of r, f dash of r times of f dash of r. Now actually we have to solve this differential equation. That's all. Got it? First you note down this. We are going to solve that as well. So from this relation, minus 2 times of f of r into f dash of r plus 2 times of f of r equal to c. R into f of r, if I take the derivative of it, then this is going to be r times of f dash of r Yeah. So if you multiply on either sides with r, and then if you take this value, so this is d by dr of r square times of f of r will be the left side and the right side will be cr. Now if you take d of r square into f of r is equal to cr dr. Now if you integrate on either sides, r square f of r is equal to c times of r square by 2 some arbitrary constant b. So this is f of r equal to c by 2 plus b by r square. Now if you take the derivative of it, f dash of r is equal to minus b by r cube. Now f dash of r, actually initially we assume this to be the acceleration. So this is equal to minus b by r cube. Then p is inversely proportional to r cube. So this is what he asked us to prove. Got it? Understood, Vishal? Understood? Yeah. The only thing is, actually when the particle is moving in a straight line from infinite, you are going to get certain velocity. When the particle is moving with central acceleration in circular path, you are going to get certain velocity. And then here actually we are equating these two, but initial thing what you need to understand is that has to be a function of r, because when the particle is moving in a straight line, the acceleration is going to be a function of r. See this, suppose actually if I leave this chalk piece and the moment the particle is at this location versus when it is moved to a distance a little bit, then the acceleration, right? So this is a function of r. So here p of r is going to be a function of r. Under gravity condition, this p of r is going to be a constant. But in all the cases it may not be. So he has given for a generalized case, when the particle is trying to move in a straight line, what will be its acceleration dependent on r. So that is p of r. This value actually he asked us to assume as f dash of r, so that you will be able to simplify easily. But if you assume as f of r, this will be a little complicated. So this is actual base thing you need to understand. Yeah. So that's all for today. So I hope actually I am done with these classes of statics and dynamics. Do you have any questions on this? Any questions? In the entire topic of statics and dynamics, I hope you fairly understood the concepts. Okay, yeah. Okay, so that's all. So maybe actually I will take off tomorrow, and day after tomorrow I will start with numerical methods. Is that fine?